Welcome back to the Explainer. Today, we're pulling some fantastic insights from Lecture 22 by Skip Uni to completely demystify complex conditional logic. You know, when we interact with software in our daily lives, it often feels like it kind of has a mind of its own, making these rapid-fire choices and adapting to our inputs instantly. But underneath all of that seamless interaction is just beautifully structured line-by-line logic. And today, we're going to break down exactly how that logic is built.
Now, think about this for a second. How does an ATM know exactly when to dispense your hard-earned cash and when to completely lock you out of your account? It's not magic, right? It's just incredibly well-written code. And today, we're going to learn exactly how that works by exploring some of the most essential control flow statements in C++. Over the next few minutes, we're going to completely master the else-if statement in C++, learn how to construct a super efficient if-else ladder in C++, and finally, we'll conquer the structure of the nested if in C++. These are literally the foundational tools that let programs make smart, dynamic decisions.
Section 1. The else-if ladder. Okay, let's dive into this. A standard if-else statement is awesome when you just have a simple choice between two specific outcomes, like pass or fail. But what happens when you've got a whole range of possibilities, yet you only want to choose a single path from those options? Well, that's exactly where the else-if ladder comes into play. Think of a classic student grading system. The program evaluates from top to bottom. If a student's marks are greater than 80%, the program prints A grade. If not, it moves down to the next rung on the ladder. Else if their marks are greater than 60%, it prints B grade. The absolutely crucial thing to remember here is the rule of one. The second the program hits the very first condition that evaluates to true, it executes that specific block of code and immediately exits the entire structure. It doesn't even bother looking at the rest.
Our source material actually makes a really fun comparison here. Dealing with an else-if ladder is a lot like dealing with the characters in that classic Indian TV serial, Office. If you've seen it, you know it's a never-ending bureaucratic runaround of multiple conditional scenarios. You know, if you have this form, go to desk A. Else, if you have that form, go to desk B. Else, come back tomorrow. The computer is basically just playing the role of that strict clerk, rigidly following the if this then that rules, until one condition is finally met. But what if you show up without any forms? Or, in our grading example, what if the student scored, say, a 40%? Well, the first if evaluates to false, the else if evaluates to false. When all those specific conditions evaluate to false, the program simply bypasses the ladder entirely and drops right into the final default else block, printing C grade. It's the ultimate safety net for your logic.
Section 2. Going deeper. Nested ifs. All right, so we just looked at the horizontal side-by-side options of a ladder. But what if your decisions are dependencies? What if you can only make decision B after you've already passed decision A? By definition, a nested if is essentially an if statement placed deep inside another if statement. It creates a strict hierarchy of conditions. If the first outer condition is true, the program doesn't just execute an action and stop. Instead, it steps a layer deeper to check the next inner condition. It's like unlocking a door, only to find another locked door right behind it. And this brilliantly illustrates our earlier question about the ATM machine. An ATM transaction isn't just one simple check. It's a hierarchical, step-by-step security gauntlet. The machine has to verify multiple things in a very specific order before it physically hands you cash. Let's break down these 4 vertical layers of code. Notice how unforgiving this outer layer is. Step 1 is the PIN check. You insert your card and type your number. If the PIN is wrong, so it evaluates to false, the program immediately kicks you out to an else block that says, wrong PIN, transaction over. But if it's true, you don't get your money yet. Passing this check simply allows the program to move a step deeper into the next if statement. Now you're in layer 2. You request 10,000 rupees. The system checks your account balance. This inner if condition asks, is the balance greater than or equal to the requested amount? If your balance is only 5,000, this inner condition fails. It immediately jumps to a nested else block, printing insufficient balance. But if you have the funds, it evaluates to true. And again, we go one step deeper. Let's move to, and see how this builds. We're now at step 3, checking your daily withdrawal limits. You might have the money in your account, but if your daily limit is 5,000 and you requested 10,000, this third if condition fails, printing exceeds daily limit. If your request is within the limit, the statement evaluates to true, and we move to the final, deepest layer. The final inner condition is the multiples check. ATMs usually only hold specific notes, right? If you entered a weird amount like 7,150, it fails this condition. But if you requested a valid multiple of 100, this final inner condition evaluates to true. You've officially passed all the nested layers. Finally, the ultimate action executes. The machine whirs and your cash is dispensed. That is the true power of the nested if.
Section 3. Comparing conditional statements. Let's briefly zoom out because choosing the right tool for the job is really what separates a beginner coder from a master. So the crucial point is understanding exactly how the compiler reads your code. On the left, we have the else-if ladder. Remember the rule of one? It picks just one path from multiple options and ignores the rest once it finds a match. On the right, we have multiple independent ifs, which is a concept from a previous lecture. Independent ifs check every single condition sequentially, regardless of whether the ones above it were true or false. They don't exit early. Understanding this theoretical difference is key to writing efficient software that doesn't waste computing power.
Section 4. Your coding assignment.
Programming is definitely not a spectator sport, so it's time to put this theory into practice. Your assignment is to build the logic for college admission eligibility software. Here are the specific rules you need to translate into code. First, if the student's stream is science and their physics, chemistry, and math marks are greater than 90%, the program should print eligible for engineering. Next, else if their stream is commerce and their account marks are greater than 90%, it should print eligible for BCom honors. Finally, if they enter anything else, the program should just fall back and print choose another course like arts.
So the final question is, how would you actually code this? Which operators will you use to combine those conditions? I highly encourage you to sit down, fire up your compiler, and try coding this logic yourself. Experiment with it, make a few mistakes, and see if you can get the correct outputs before we discuss the solution in our next explainer. Keep practicing, and I'll see you next time.